All right, welcome everyone for another seminar of Young Research of Quantum Gravity. Today we have Suzanne Bintanja. Suzanne is a PhD student at the University of Amsterdam, where she also did her bachelor and her master degree. She works in Amsterdam with supervisor Alejandro Castro, and she's working on topics like conformal field theory, symmetric product orbifold theories, but also wormholes. As a matter of fact, last month I saw she brought out a paper about tunneling to holographic transferable wormholes, so make sure to check it out. And today she will talk about the Toolbox for Holographic CFT. Suzanne, thank you for accepting the invitations, and the floor is yours.
Awesome. Thanks for the nice introduction and for the invitation to speak. Unfortunately, I'm not going to talk about the paper that we put out last month, but be sure to check it out. And if you have questions about it, I'm happy to answer those as well. But today I wanted to tell you guys a little bit about some stuff that I've been thinking about the last few years. And I came up with this title. And the thing that I hope that you take away from this talk is that with very simple arguments, we can learn a lot about gravity. So yeah, this talk will be based on these 3 papers that I've listed. And I should also thank my collaborators, Luisa Polo, Alex Bellin, Alejandro Castro, Christoph Keller, Nathan Benjamin, and Yilda Hollander, without whom these papers wouldn't have been there. Yeah, also feel free to ask questions anytime. I'm happy to answer them, and I hope everyone can follow along. So if anything is unclear, please let me know. All right, let's see, how do I go on? So the plan of the talk will be like this. We roughly have 4 parts, and so you can track along how many slides we still have to go. But let's not waste too much time and just get into it. So the question that I've been mainly thinking about, the big picture question, is how can we find UV complete theories of quantum gravity? And if we find them, what flavors do they come in? So what are things that are universal and that are true for any such theory, and what are things that are different and depend on the theory? And in recent years, a lot of progress has been made using the ADS-CFT correspondence, and that's also the arena that we will be in today. So let me very briefly remind people what it is about. I hope most of you have seen some of it, but the statement is as follows. So in theories that have a negative cosmological constant, the rules to obtain a theory of quantum gravity are clear. The observables are correlation functions of local operators that you insert at the asymptotic boundary of this universe with negative cosmological constant. And those correlation functions satisfy the axioms of conformal field theory. So they should be unitary, they should satisfy causality, and also crossing symmetry. And the picture that people often draw, and that I decided to draw as well, is that of the cylinder. So the way that you should think about it is that the inside of the cylinder is this universe with negative cosmological constant, ADS, and it has gravity inside it. And observables, which I drew here, some 4-point function on a time slice t here. So the observable is some scattering process between operators that you insert at the boundary of the cylinder. And the scattering process, it will involve like graviton exchange or maybe matter exchanges, whatever is in this theory of quantum gravity. So there's some gravitational process going on in here. And the statement of ADS-CFT is that you can describe any such process with the physics of a CFT that lives on the boundary of this cylinder, which has 1 dimension less. And the way that you can see that, or one very simple way to see is that gravity is actually dynamical in this universe, is the fact that the conformal field theory, it contains a conserved stress tensor. And in the ADS dual, that corresponds to a massless graviton that gives rise to the gravitational physics. And the perspective that we will take today is that just by looking at the CFT, this will define for us the physics in gravity. So the point of view is that you take any CFT that you like, you put it on the cylinder, and just by computing the correlation functions in that CFT, you can find the answers about this putative gravitational theory that lives on the inside of the cylinder. So again, any CFT defines a theory of quantum gravity in ADS. However, generically, that theory of quantum gravity doesn't really look much like gravity as we know it in our universe. First of all, generically, there's no semiclassical description, so quantum effects are very big. And there is also no low energy effective description of general relativity weakly coupled to matter. Generically, the gravitational theory that lives on the inside of the cylinder is highly quantum and highly non-local. But I want to insist on theories that do have a nice description in their bulk. So more precisely, we will insist on theories that have a low energy effective description of semiclassical general relativity, plus weakly coupled, possibly interacting matter. So what that means is that we want the gravitational theory to have a low energy effective action of this form. And the first term here, hopefully you will recognize as the Einstein-Hilbert term with cosmological constant that we will take to be negative. And the second term is some matter action where the matter fields are weakly coupled or minimally coupled to the metric. Here I wrote it for a scalar field, but it can also be other fields. And we will call CFTs who define such nice gravitational theories holographic. So if you take any quantum field theory, it's already quite special that it is conformal. It has to satisfy way stronger conditions. And then on top of that, we will insist that the CFT is also holographic. So there's additional constraints that we impose on the CFT. And those I will review in the next few slides, or some of those I will review. So the first additional constraint that a holographic CFT should satisfy is that there is a large n limit. And that means that there is a parameter that we will call n, which is way bigger than 1, such that the stress tensor 2-point function scales in this particular way. And just for future conventions, I will normalize 2-point functions that are not the stress tensor or that are not fixed by the conformal algebra to have unit 2-point function and to be diagonal. So if OI is not the same as OJ, the 2-point function will vanish. And when we take this parameter n very large, the spectrum splits into at least 2 regimes. First of all, there is the set of light operators who have scaling dimensions that don't depend on this n. And also, very importantly, correlation functions of these light operators are not allowed to scale with n. They are finite if we take n to infinity. And the second regime that should always be there is the regime of heavy operators with scaling dimension above some threshold that I won't specify here, but that threshold usually scales with n. In particular, operators that have a scaling dimension linear in n are usually called black hole microstates. And this large n limit in the CFT, it corresponds in the gravitational theory to the fact that quantum effects are small, which was shown
Hello.
in this paper. Yes?
Can I ask a question? Yeah. So actually, I'm confused about this n, large n. What do you mean by n? Like, which parameter are you talking about? Like the n in the gauge group n, or
I will come back to that later. At this point, we are super generic. I'm just saying there is some parameter whose that is equal to the 2-point function of the stress tensor divided out by x to the 2d. We will come back to specific examples.
oh, thank you.
And we have also a question in the chat. Would you also like to answer that right now, or shall we do that afterwards?
Yeah, we can do it now.
So the question is from Deepan Batal, and he asks, can we have ADS with different topologies, and are there different holographic CFTs for different topologies?
I would say that right now I'm insisting on having this cylinder. I don't know exactly what you mean with different topologies. Like, do you mean that you want to have a black hole inside, or you want to put it on a torus? Maybe we can discuss later. But I want this picture to be true. All right. So that was the large n limit. If there's no further question, let me continue to the second condition that I want to impose. The second condition is usually called large n factorization. And what it means is that there is a subset of light operators that factorize when we take the limit n to infinity. This subset can be all light operators, or it can be some smaller set, and that will be important later in the talk. And again, just as before, this set of light operators that factorize split into two types of operators. First of all, we have single trace operators that I will denote in this way with the lower index, which denotes what operator we are talking about. And these single trace operators behave as generalized free fields when we take n to infinity. More precisely, if I look at the connected component of the correlation function of J single trace operators, it scales in this way with n. And so you see for a 2-point function, it will scale like n to the 0, just as our conventions that I just discussed. But when you look at higher point functions, each extra insertion of a single trace operator causes the correlator to be suppressed by a factor of 1 over square root n. So indeed, these operators behave as free fields when we take n to infinity. Interactions are suppressed. And in particular, say that we have, we consider a correlation function of an even number of operators, say 2j. And we look at not just the connected component, but the whole thing. Then the leading order contribution will be that where the correlator splits up into different factors of 2-point functions. So because these are 2-point functions, they don't scale with n. And so these contributions plus permutations where we put different operators in different factors, they don't scale with n, and all other contributions are suppressed in n. All right, very good. And in the gravitational theory, what this large n factorization implies is that gravity is weakly coupled. So in particular, we want the stress tensor, which is dual to the graviton, to also behave in this way. So the 4-point function of a stress tensor is its leading order contribution comes from the product of 2-point function of stress tensors. All right, very good. So this was the first type of operators in the factorizing subset. The second type of operators are called multi-trace operators. I will denote them as O with some higher index, k, and this k denotes the number of traces. And you can define these multi-trace operators by the fact that there are k single trace operators, so that this connected correlation function of OK together with the k single trace operators does not scale with n when we take n large. And once you start thinking about this, you realize that these multi-trace operators are nothing but normal ordered products of single trace operators and descendants thereof. And you can see that this should be the case because when we look at the connected correlation function of a normal ordered product of O1 through OK together with O1 and X1, blah, 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 until OK of XK, sorry, this should be a K. It splits up again into a product of 2-point functions, but now because these O1 through OK in the normal ordered product are all at the same insertion point, this term is in fact part of the connected correlator. And it is very easy to see that this term is order 1. So these are the multi-trace operators, and what you should take away from this slide is that you can determine for these factorizing operators, you can determine the leading order scaling of correlation functions by doing these Wick contractions, is what this is called. And you will find the leading order term by Wick contracting as much as possible. Yes. All right. Very good. So that was the second condition. Then the third condition for that a holographic CFT has to satisfy is the so-called large gap condition, which says that there is a large gap for single trace higher spin operators. Here's what that means. So the scaling dimension of these higher spin single trace operators is larger or equal than some delta gap, some number, which is parametrically larger than 1. And it was conjectured in this landmark paper, the HPPS paper, that once you have this large gap, then the effective field theory in the bulk dual is local. And this was proven when we take delta gap to be infinity. And when delta gap is parametrically large, these people have found bounds on the higher derivative operators as a function of this delta gap that show that when you take delta gap to be larger and larger, the non-localities go away. Very good. And then the final condition that I will discuss right now is the so-called sparse spectrum condition, which says that there should be a very sparse spectrum of light operators. That means that the density of states for states with scaling dimension below some bound, here I wrote the bound for d equals 2, but there are similar bounds for other dimensions. So the density of states for those states should scale like this. So e to the delta to the gamma, where gamma is strictly less than 1. And in the gravitational theory, this makes sure that the degeneracy in the conformal field theory, it reproduces the Bekenstein-Hawking entropy for black holes. And it is, in addition, consistent with a light spectrum of supergravity or general relativity. So these are 4 conditions that are necessary to have a holographic CFT, to have a bulk dual that has a low energy effective description of general semiclassical general relativity. But it is unclear whether these conditions are sufficient and if they are independent. So that's, I think that's a very interesting research avenue, and I've been thinking about it quite a bit. All right, so that was what I wanted to say about holographic CFTs. Are there any questions before we continue? All right, then let's continue. Let me give some examples of theories, conformal field theories that satisfy some of the requirements that we just reviewed. And we know many examples of CFTs that satisfy the first and second conditions. So they have a large n limit and they satisfy large n factorization. The most well-known example that already came up in a question is the example of large n gauge theories. The most famous example is n equals 4 super Yang-Mills, which was the original instance of ADS CFT. Here, the large n limit is the 't Hooft limit, and large n factorization, it's you can see it or it's equivalent in the language of gauge theories as the planar expansion. Then there are also ON vector models that show up, for example, in ABGM that have a large n limit. All right, I should say that in these gauge theories, the gauge group is SUN, and that is the n that we take to be large. Same for the vector models whose symmetry group is ON. And then the final example or class of examples live in 2 dimensions, and they are symmetric product orbifolds or permutation orbifolds. And these papers showed that these theories have some factorizing set of operators. And one property of all the examples that I've listed above, and as far as I know, in all examples that were known until very recently, there's not just a subset of light operators that factorizes, actually the entire light spectrum factorizes. So any light operator, it will behave as a generalized free field when we take n to be large. And on the one hand, this is a very nice property because it gives us an organizational principle and it allows us to do computations because we know very well what are leading contributions, and we have a weakly coupled conformal field theory. One maybe slightly less appealing consequence of the fact is that all interactions in those CFTs happen at the Planck scale. And you can see that by translating this n to gravitational parameters. That's done in this way. So you see that n is inversely proportional to Newton's constant. And so when interactions are suppressed with n in the gravitational theory, that means that the coupling constants have power of g Newton. So not just gravity will be weakly coupled, but any matter field that will live in the dual gravitational theory will only interact at the Planck scale, which is not what we see in our universe. And so it will be interesting to see whether we know any theories that, or whether we can understand theories that don't have this property. Moreover, all the examples that I mentioned in the last slide contain infinite towers of higher spin currents due to the symmetry group scaling with n. So for the gauge theories and the ON vector models, this is very clear because the symmetry group is SUN and ON. In symmetric product orbifolds, the symmetry group is roughly Vera0 to the tensor power n mod Sn. So also that group scales with n. And this implies that, or well, this shows that the large gap condition is not satisfied, and also these theories don't have a sparse spectrum. And so their gravitational duals are non-local and very stringy. And also, like I mentioned before, they only interact in a Planck scale, at the Planck scale. And so for us, that was sort of the starting point to look for a mechanism to turn on the string tension and get rid of this non-locality, and to look for a mechanism to add interactions, to use these conformal field theories that have very attractive properties in terms of holography, to use them as a starting point and to get to theories that are even more compatible with things that we see outside. But one very important feature is that we still want gravity to be weakly coupled. So we want to deform the theory, but in such a way that this nice property remains satisfied. Very good. That brings me to the third part. Are there any questions before we continue? All right. So we look for a mechanism to turn on the string tension and to turn on interactions. And one way to do that is to deform these factorizing conformal field theories by an exactly marginal operator. And now you should imagine that is that you have your original CFT and you add this delta S term to it. Not any CFT can be written in terms of as an action, but this adding this deformation still makes sense. Is there a question?
Oh, no, sorry. I could hear you anymore for a moment, but maybe it might probably be on my side.
All right. Let me know if there's any issues at any point. So there's two parameters that are important. Here there's lambda k, where lambda is some order 1 number that is the coupling constant. That doesn't scale with n, very importantly. And there can be some n scaling with the power beta. And this beta we will study in a moment. And then we add an exactly marginal operator, OK, a k-trace operator in general, and we integrate over its insertion. And here the operator OK is exactly marginal, which means that its scaling dimension is equal to the number of dimensions independent of the value of the coupling constant. And the fact that OK is exactly marginal, it implies that adding this term delta S to the theory does not break conformal symmetry. So for any value of lambda k, the theory that we end up with is still conformal. And that means that we have a conformal manifold with the coordinates of this manifold being the values of lambda k. And at each point on this manifold, we have a CFT, and the CFTs can have different properties at different points on the manifold. But let's look a little bit more precisely at how such a CFT at a certain point on the manifold looks like. So you can compute correlation functions at any point on the conformal manifold that I denote by the coordinates lambda k or by the coupling constant lambda k in the following way. So you just have the original correlation function in the undeformed theory, and you add this e to the delta s, and you also normalize with e to the delta s. And this hopefully looks quite familiar from quantum field theory, where you would do exactly the same thing. And we can expand out when lambda k is not too large, we can expand out the exponential and explicitly see what the deformation does to the theory. So first you have just the original correlation function, and then there are corrections that scale with lambda and lambda squared, etc. What shows up is the n scaling, just as before. And now we have a correlation function the connected component of a correlation function with the original insertions plus an added insertion of the deformation operator. And we integrate over that coordinate. And the higher in order you go, the more insertions of the deformation operator you get. In particular, the spectrum of the theory can depend on lambda. And the way to see that is to look at the two-point function at a generic point in the moduli space. So because the theory is conformal, we know that the two-point function has a very simple form, just this form, where the weight h can depend on lambda. And let's split this weight into the weight at the underformed theory, so at lambda equals to 0, plus some anomalous dimension that we will call gamma. Then you expand in gamma, and you see that precisely the anomalous dimension, you can find it by computing this two-point function and looking for a term that scales with log z. Very good. So we can compare that to the expansion that I just wrote down on the previous slide. So the two-point function in the deformed theory, it's equal to the two-point function in the underformed theory plus these correction terms. And so the way to determine the spectrum of a deformed theory is to compute these quantities and look for terms that scale with log of z. And that coefficient in front of that log, it will give you the anomalous dimension. And so these deformations, hopefully, or the hope is that these deformations can be used to get rid of the higher spin symmetry that is present in the factorizing CFTs, and also to create this sparse spectrum. All right, so depending on the values of the parameters beta and k, so the n scaling and the number of traces of the deformation operator, we can have different effects. And the first effect, or the first thing that I want to discuss, is that even after the deformation, I still want to have a consistent large n limit. I don't want to break the nice properties that we had before. And if you remember, what that means is that correlation functions of light operators should be finite when we take n to infinity. So let's investigate what that means. So we look at a correlation function in the deformed theory. Well, this term is fine. This is just the correlation function in the underformed theory, and we know that that one is finite. But then we go look at the correction terms. Now this correlation function is a correlation function of light operators. We evaluate it at the underformed point, so it is finite when we take n to infinity. And so as long as we don't put a positive power outside, we are still good, and we can safely take n to infinity. So beta less or equal than 0 is good. But when k equals to 1, so when we deform by a single trace operator, we can do a little bit better. Because if you remember, the connected correlation function of single trace operators, it is suppressed in powers of n, and with each insertion, there's a further suppression of 1 over square root n. So if k equals to 1, this correlation functions, or these types of correlation functions, are suppressed with a square root n compared to this first contribution. And thus we can, in this special case, put beta equals to 1 outside. So just to summarize, beta less or equal to 0 is always okay. But when we consider single trace operators, we can also put beta equals to 1. Very good. Then the second effect that we are interested in is the lifting of unprotected operators. So as I said just before, we want to investigate whether we can use these deformations to satisfy the other holographic properties as well. So the large gap property and the sparse spectrum property. And to do that, we need to get large anomalous dimension for many operators, for generic operators, in fact. So to investigate, let's look at the 2-point function and how it changes under the deformation. And so what we need is that for generic O's, for generic choices of O here, this quantity should not be suppressed. But for let's pick some generic O. In fact, to have the worst case scenario is that, or worst case scenario is maybe not the correct way to say it, but generically, this O will not be an O that appears in the deformation operator, in the normal ordered product of our K-trace deformation. So in that case, we cannot Wick contract this correlation function. And so adding the deformation operator, it will lead to a suppression in N. So if we don't enhance the scaling, so if beta is less or equal than 0, this is no good, and we will not be able to lift generic operators in the theory. And so to get large anomalous dimensions for many operators, we need beta equals to 1, and we just saw that that implies that we should deform by single trace operators. So like I said, for beta less or equal than 0, generically anomalous dimensions are small, and to have any hope to get to a holographic CFT that satisfies all the conditions, we need to deform with beta equals to 1, and we need to deform with a single trace operator. And this is precisely the scaling that is used in the well-known example of the D1, D5 system. If you have never heard of it, that's fine, but it's just an example where this scaling was used, and it was shown that it does exactly that, that it leads to a holographic point. Even more so, we showed in some of the papers that this talk is based on, that when you are in 2 dimensions, using this particular scaling, you break the entire higher spin theory of the undeformed theory.
Suzanne, sorry to interrupt. We have here an anonymous question, sorry, asking what is meant with deformation. So maybe if you could clarify a little bit the idea.
All right. Yeah, let me go back a few slides where I defined the deformation. So basically, this is the deformation. You start with your generic CFT, and then you add to it this term, or you imagine adding this term to the action. What it means in terms of the correlators is the following. So any correlation function in the deformed theory is defined by this quantity. And then you can expand it and, well, do the things that I explained.
I think that should be enough. Thank you, Suzanne.
Yeah, no worries. All right. I think this is where we were. Very good. So the hope is that we can use this particular scaling and these types of deformations to obtain theories that not just have a large n limit and large n factorization, but also have a large gap and a sparse spectrum. This is very hard to check in perturbation theory because you have to go many orders to see any very large effect. But one thing that is very useful is that there are quantities that you can compute in the CFT that are constant, that are a constant function, that are constant as a function of these coupling constants. So they are constant functions of lambda. And so that means that I can compute these quantities anywhere on a conformal manifold that I want, and I will know the answer everywhere on a conformal manifold. So in particular, at the point where we have very good control, where we have a large n limit and large n factorization, we can compute these quantities. And if there is any hope that a deformation leads to a holographic CFT, these types of quantities better be consistent with having a holographic CFT. And that is one tool that we used quite a bit. So that is something that you can do to make non-perturbative statements. Very good. And then the final property that I want to discuss is large n factorization. And the argument is a little bit too involved to do now. But if you sit down and you figure out the scaling of these correlation functions just by doing Wick contractions, you will find that if we pick beta less or equal than 2 minus the number of traces, this means that the deformed theory remains fully factorized. And the way that you investigate is that you figure out what value of beta you should put, such that the leading order scaling of correlators is unchanged. And so this opens up an interesting range where we pick beta to be bigger than this bound, so between 2 minus k and less than 0, where the deformed theory still has a consistent large n limit, but the factorization is broken. And these are a set of deformations that were not really studied before. So let me recap. There are, you can deform the theory, or you can deform a CFT with a single or a multi-trace deformations, and both of these types of deformations have very different effects. If you deform by a single trace operator with beta equals to 1, you can lift operators from the spectrum, and you can possibly find a holographic CFT. However, you can never turn on interactions because when k equals to 1, you can never not satisfy this bound and still have a good large n limit. The other thing that you might be interested in is to turn on interactions. And to do that, you need multi-trace deformations. Single trace operators won't do that for you. So you have sort of these linearly independent effects or directions on the conformal manifold that you can do. All right, very good. That's what I wanted to say about conformal manifolds. Let's see, how are we doing on time? Maybe not great. All right, so let me continue very quickly by giving an example and showing some simple calculation that shows how these computations go. Any questions before we do that? All right, let's go. So I want to consider a triple trace deformation, so a multi-trace deformation, and we want to see how these kinds of deformations break factorization, if and how they do that. So just for concreteness, we consider a two-dimensional conformal field theory with n equals 2 supersymmetry. And the reason that we want to do that is because in those theories, I know very well, or we know very well, how to find these exactly marginal operators that we can deform by. And on top of that, I want to insist that the theory that we consider has a chiral primary with this particular scaling dimension. And the reason that I'm insisting of this on this scaling dimension is that using this chiral primary O, I can make an exactly marginal triple trace deformation in precisely this way. And here G, the G's are the supercurrents that are the super partner of the stress tensor. And so we have a triple trace exactly marginal operator that we can use to deform the theory. And also, let me say that these CFTs exist. We know of infinitely many two-dimensional CFTs that have this chiral primary operator and thus that have this deformation or this exactly marginal operator. And let me just remind you that in a completely factorizing CFT, which is our starting point, the OPE coefficient, or the three-point function of single trace operators, scales with 1 over square root n. And then we will study how the OPE coefficients change as we turn on this triple trace deformation. And just by writing out the definition of the deformation and how that changes three-point functions, we see that the OPE coefficient of single trace operators, it changes in this way under the deformation with O3. So there's this n to the beta over 2 outside, and we have this connected now 4-point function with the 3 single trace operators inside, and we integrate over the insertion of the multi-trace deformation. And this integral is formally divergent, but we can regularize it. So we take b equals to beta equals to 0, the value for which we can break large N factorization, and we will pick the operators, the operator OI to be chi, which is just a shorthand notation for this operator, and we pick OJ and OK to be equal to O. So for this specific example, we can compute this 4-point function. And when we write out the O3, this is what it looks like when we properly normalize. And just by doing the Wick contractions, like we've been using them this whole time, we can quickly and very easily find the leading order contribution to this 4-point function. And you can already see why I insisted on this choice of operators, because this particular OPE coefficient of chi, O, and O is precisely the one where we can, it's the only one where this 4-point function is order 1 and not suppressed in N. And in fact, when you write out this Wick contraction, you get this very simple formula. Very good. So if we plug that back into the formula that we found for the change in the OPE coefficient at lambda equals to 0, we just have to do this integral over x, and that will give us the leading order change in the OPE coefficient. And this integral is one that you can do. You have to regulate in some way, but that can be done, and you find this this answer. And this is really amazing. This is a really amazing result, and I really want to stress it. We started with an OPE coefficient COO chi that was suppressed in n. It's scaled with 1 over square root n. Now we add this deformation of lambda, and we get a result that is finite as we take n to infinity. Therefore, we have turned on an interaction by doing this deformation. But one other thing that we should really keep in mind is that this is the only single trace OPE coefficient that is finite as we take n to infinity. Remember, we had to pick our operators OI, OJ, and OK very carefully in order to be able to do this with contraction and get the order 1 result. So the deformation breaks large n factorization, but in a very controlled way. We are not messing, we are not breaking, well, we are breaking the nice structure of large n factorization, but in a very minimal and controlled way, and we can keep track of how we break it. So yeah, that's really a great, amazing result, and we could do it with a very simple calculation. So let me very quickly conclude. So I hope that the thing that you take away from this talk is that in order to obtain a theory of quantum gravity with low energy effective description of weakly coupled semiclassical general relativity and interacting matter, you need a two-step process. You start with a free factorizing CFT, of which we know many examples. And first you deform it with a single trace operator to a holographic CFT, which we have many pieces of evidence that this is what happens, even though it's very hard to show. And then secondly, you turn on a multi-trace deformation with this scaling to turn on the interactions within the matter sector. And this can be done in a very controlled way, as we just showed in our example. And yeah, finally, let me stress one more time that we could figure all of this out by just counting, basically. So you don't need any super sophisticated arguments to already learn a lot of things about gravity. So thanks.
Thank you very much, Suzanne. So we can stop the recording.